Offshore wind power refers to the construction of wind farms in bodies of water to generate electricity from wind. Stronger wind speeds are available offshore compared to on land, so offshore wind power a Euro unregistered trademark's contribution in terms of electricity supplied is higher, and NIMBY opposition to construction is usually much weaker. However, offshore wind farms are relatively expensive. At the end of 2012, 1,662 turbines at 55 offshore wind farms across 10 European countries were generating electricity enough to power almost 5 million households. As of 2010, Siemens and Vestas were turbine suppliers for 90% of offshore wind power, while Dong Energy, Vattenfall and E.on were the leading offshore operators. As of October 2010, 3.16 gigawatts of offshore wind power capacity was operational, mainly in Northern Europe. According to BTM Consult, more than 16 GW of additional capacity will be installed before the end of 2014, and the United Kingdom and Germany will become the two leading markets. Offshore wind power capacity is expected to reach a total of 75 GW worldwide by 2020, with significant contributions from China and the United States. As of 2013, the 630-megawatt London Array is the largest offshore wind farm in the world, with the 504 Greater Gabbard wind farm is the second largest, followed by the 367 MW Walney wind farm. All are off the coast of the UK. These projects will be dwarfed by subsequent wind farms that are in the pipeline, including Dogger Bank at 7,200 MW, Norfolk Bank, and Irish Sea. At the end of June 2013, total European combined offshore wind energy capacity was 6,040 MW. UK installed 513.5 MW offshore wind power in the first half year of 2013. Definition: offshore wind power refers to the construction of wind farms in bodies of water to generate electricity from wind. Unlike the typical usage of the term offshore in the marine industry, offshore wind power includes inshore water areas such as lakes, fields and sheltered coastal areas, utilizing traditional fixed-bottom wind turbine technologies, as well as deep water areas utilizing floating wind turbines. A subcategory within offshore wind power can be nearshore wind power. History: Europe is the world leader in offshore wind power, with the first offshore wind farm being installed in Denmark in 1991. In 2013, offshore wind power contributed to 1,567 MW of the total 11,159 MW of wind power capacity constructed that year. By January 2014, 69 offshore wind farms had been constructed in Europe with an average annual rated capacity of 482 MW in 2013, and as of January 2014 the United Kingdom has by far the largest capacity of offshore wind farms with 3,681 MW. Denmark is second with 1,271 MW installed, and Belgium is third with 571 MW. Germany comes fourth with 520 MW, followed by the Netherlands, Sweden, Finland, Ireland, Spain, Norway and Portugal. By January 2014, the total installed capacity of offshore wind farms in European waters had reached 6,562 MW. As of January 2014, German wind turbine manufacturer Siemens Wind Power and Danish wind turbine manufacturer Vestas together have installed 80% of the world's 6.6 GW offshore wind power capacity. Senvion Ratepower comes third with 8% and Bard. Projections for 2020 calculate a wind farm capacity of 40 GW in European waters, which would provide 4% of the European Union's demand of electricity. The Chinese government has set ambitious targets of 5 GW of installed offshore wind capacity by 2015 and 30 GW by 2020 that would eclipse capacity in other countries. In May 2014, current capacity of offshore wind power in China was 565 MW. India is looking at the potential of offshore wind power plants, with a 100 MW demonstration plant being planned off the coast of Gujarat. In 2013, a group of organizations, led by Global Wind Energy Council, started Project VOWIN to identify potential zones for development of offshore wind power in India and to stimulate O&D activities in this area for wind. In 2014, Wind commissioned Center for Study of Science, Technology and Policy to undertake pre-feasibility studies in 8 zones in Tamil Nadu which have been identified as having potential. Farms. At the end of 2011, there were 53 European offshore wind farms in waters off Belgium, Denmark, Finland, Germany, Ireland, the Netherlands, Norway, Sweden and the United Kingdom, with an operating capacity of 3,813 MW, while 5,603 MW is under construction. More than 100 GW of offshore projects are proposed or under development in Europe. The European Wind Energy Association has set a target of 40 GW installed by 2020 and 150 GW by 2030. As of July 2013, the 175-turbine London Array in the United Kingdom is the largest offshore wind farm in the world with a capacity of 630 MW, followed by Greater Gabbard, also in the United Kingdom, Onholt in Denmark, and Bard Offshore 1 in Germany. There are many large offshore wind farms under construction including Gwynt Waimea, Balcombe West 2, and west of Dudon Sands. Offshore wind farms worth some $8.5 billion were under construction in European waters in 2011. Once completed, they will represent an additional installed capacity of 2,844 MW. China has 2 operational offshore wind farms of 131 MW and 101 MW capacity. Canadian Wind Power in the province of Ontario is pursuing several proposed locations in the Great Lakes, including the suspended Trillium Power Wind 1 approximately 20 km from shore and over 400 MW in capacity. Other Canadian projects include one on the Pacific West Coast. As of 2012, there are no offshore wind farms in the United States. However, projects are under development in wind-rich areas of the East Coast, Great Lakes, and Pacific Coast. In January 2012, a Smart for the Start regulatory approach was introduced, designed to expedite the siting process while incorporating strong environmental protections. Specifically, the Department of Interior approved a Air Wind Energy Euro off the coast where projects can move through the regulatory approval process more quickly. The first offshore wind farm in the USA is expected to be the 30-megawatt, 5-turbine Block Island project, which is scheduled to be online in late 2016. Economics and benefits. Offshore wind power can help to reduce energy imports, reduce air pollution and greenhouse gases, meet renewable electricity standards, and create jobs and local business opportunities. However, according to the U.S. Energy Information Agency, offshore wind power is the most expensive energy-generating technology being considered for large-scale deployment. The advantage is that the wind is much stronger off the coasts, and unlike wind over the continent, offshore breezes can be strong in the afternoon, matching the time when people are using the most electricity. Offshore turbines can also be located close to the power-hungry populations along the coasts, eliminating the need for new overland transmission lines. Most entities and individuals active in offshore wind power believe that prices of electricity will grow significantly from 2009, as global efforts to reduce carbon emissions come into effect. BTM expects cost per kilowatt-hour to fall from 2014, and that the resource will always be more than adequate in the 3 areas Europe, United States and China. The current state of offshore wind power presents economic challenges significantly greater than onshore systems. Prices can be in the range of €1,000,000 per MW. The turbine represents just 1/3 to 1/2 of costs in offshore projects today, the rest comes from infrastructure, maintenance, and oversight. Larger turbines with increased energy capture make more economic sense due to the extra infrastructure in offshore systems. Additionally, there are currently no rigorous simulation models of external effects on offshore wind farms, such as boundary layer stability effects and wake effects. This causes difficulties in predicting performance accurately, a critical shortcoming in financing billion-dollar offshore facilities. A report from a coalition of researchers from universities, industry, and government, lays out several things needed in order to bring the costs down and make offshore wind more economically viable, improving wind performance models, including how design conditions and the wind resource are influenced by the presence of other wind farms. Reducing the weight of turbine materials, eliminating problematic gearboxes, turbine load mitigation controls and strategies, turbine and rotor designs to minimize hurricane and typhoon damage, economic modeling and optimization of costs of the overall wind farm system, including installation, operations, and maintenance, service methodologies, remote monitoring, and diagnostics. Research and development projects aim to address these issues. One example is the Carbon Trust Offshore Wind Accelerator, a joint industry project, involving 9 offshore wind developers, which aims to reduce the cost of offshore wind by 10% by 2015. It has been suggested that innovation at scale could deliver 25% cost reduction in offshore wind by 2020. In 2011, a Danish energy company claimed that offshore wind turbines are not yet competitive with fossil fuels, but estimates that they will be in 15 years. Until then, state funding and pension funds will be needed. Bloomberg estimates that energy from offshore wind turbines cost €161 per megawatt-hour. A comprehensive review of the engineering aspects of turbines, like the sizes used onshore, including the electrical connections and converters, considers that the industry has in general been over-optimistic about the benefits costs ratio and concludes that the offshore wind market does an unregistered trademark T look as if it is going to be big. In Belfast, the harbour industry is being redeveloped as a hub for offshore wind farm construction, at a cost of about £50 million. The work will create 150 jobs in construction, as well as requiring about 1 m tons of stone from local quarries, which will create hundreds more jobs. It is the first dedicated harbour upgrade for offshore wind. As the first offshore wind farms move beyond their initial warranty periods with the turbine equipment manufacturer, an increase in alternative operations and maintenance support options is evident. Alternative suppliers of spare parts are entering the market, and others are offering niche products and services, many of which are focused on improving the power production volumes from these large renewable energy power plants. Technical details: in 2009, the average nameplate capacity of an offshore wind turbine in Europe was about 3 MW, and the capacity of future turbines is expected to increase to 5 MW. Offshore turbines require different types of bases for stability, according to the depth of water. To date, a number of different solutions exist. A monopile base, 6 meters in diameter, is used in waters up to 30 meters deep. Gravity-based structures, for use at exposed sites in water 20-80 m deep. Tripod-piled structures, in water 20-80 meters deep. Tripod suction caisson structures, in water 20-80 m deep. Conventional steel jacket structures, as used in the oil and gas industry, in water 20-80 m deep. Floating wind turbines are being developed for deeper water. Turbines are much less accessible when offshore, and thus reliability is more important than for an onshore turbine. A maintenance organization performs maintenance and repairs of the components, spending almost all its resources on the turbines. Some wind farms located far from possible onshore bases have service teams living on site and offshore accommodation units. Because of their remote nature, prognosis and health monitoring systems on offshore wind turbines will become much more necessary. They would enable better planning just-in-time maintenance, thereby reducing the operations and maintenance costs. According to a report from a coalition of researchers from universities, industry, and government, making field data from these turbines available would be invaluable in validating complex analysis codes used for turbine design. Reducing this barrier would contribute to the education of engineers specializing in wind energy. The planning and permitting phase can cost more than $10 million, take €7 years, and have an uncertain outcome. The industry puts pressure on the governments to improve the processes. In Denmark, many of these phases have been deliberately streamlined by authorities in order to minimize hurdles, and this policy has been extended for coastal wind farms with a concept called a unregistered trademark one-stop shop, a unregistered trademark. USA introduced a similar model called SMART from the start in 2012. Some of the guidelines for designing offshore wind farms are IEC 61400-3, but in the US several other standards are necessary. The standards requires that a loads analysis is based on site-specific external conditions such as wind, wave and currents. Design environment equals. Offshore wind resource characteristics span a range of spatial and temporal scales and field data on external conditions. For the North Sea, wind turbine energy is around 30 kilowatt-hours per meter cube of sea area, per year, delivered to grid. The energy per sea area is roughly independent of turbine size. Necessary data includes water depth, currents, seabed, migration, and wave action, all of which drive mechanical and structural loading on potential turbine configurations. Other factors include marine growth, salinity, icing, and the geotechnical characteristics of the sea or lake bed. A number of things are necessary in order to retain the necessary information on these subjects. Existing hardware for these measurements includes light detection and ranging, sonic detection and ranging, radar, autonomous underwater vehicles, and remote satellite sensing, although these technologies should be assessed and refined, according to a report from a coalition of researchers from universities, industry, and government, supported by the Atkinson Center for a Sustainable Future. Because of the previous factors, one of the biggest difficulties with offshore wind farms is the ability to predict loads. Analysis must account for the dynamic coupling between translational and rotational platform motions and turbine motions, as well as the dynamic characterization of mooring lines for floating systems. Foundations and substructures make up a large fraction of offshore wind systems, and must take into account every single one of these factors. Corrosion is also a serious problem and requires detailed design considerations. The prospect of remote monitoring of corrosion looks very promising using expertise utilized by the offshore oil gas industry and other large industrial plants. Environmental impact. While the offshore wind industry has grown dramatically over the last several decades, especially in Europe, there is still a great deal of uncertainty associated with how the construction and operation of these wind farms affect marine animals and the marine environment. Common environmental concerns associated with offshore wind developments include the risk of seabirds being struck by wind turbine blades or being displaced from critical habitats, the underwater noise associated with the installation process of driving monopile turbines into the seabed, the physical presence of offshore wind farms altering the behavior of marine mammals, fish, and seabirds with attraction or avoidance, the potential disruption of the near-field and far-field marine environment from large offshore wind projects. The TETHIS database provides access to scientific literature and general information on the potential environmental effects of offshore wind energy. See also, List of offshore wind farms, lists of offshore wind farms by water area. References. External links, media related to offshore wind power at Wikimedia Commons, updated capacity statistics at LOSE, TETHIS database, a database of information on potential environmental effects of marine, hydrokinetic, and offshore wind energy development.